Hi, this is Foundations of Math and Pre-Calculus 10, Chapter 4.2. This time we'll be looking at integral exponents. And rather than expanding powers and counting, it's better to develop rules to multiply and divide powers. There are no general rules to add or subtract powers. And recall that this is a power. This is the base, and this is the exponent. So please try to use the correct terminology when you're referring to the whole thing, or just the base, or just the exponent. So let's look at examples to see if we can develop some rules. And if you forget these rules on a test, you can always derive them just as we are here. Okay, we are doing 5 cubed to the power of 4. So this is 5 cubed times 5 cubed times 5 cubed times 5 cubed. So 4 times. And if we expand the cubes, we get 5 times 5 times 5, 5 times 5 times 5, 5 times 5 times 5, 5 times 5 times 5. Okay, this gets very repetitive and very lengthy. How many 5s do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is 5 to the power of 12. However, what's the rule? This is 3 times 4 using our original numbers. Okay? So, power of a power we multiply the exponents. Okay, let's look at the next one. This is 5 cubed times 5 to the power of 4, and let's just expand it. 5 times 5 times 5, 5 times 5 times 5 times 5. Okay, and this is 1, 2, 3, 4, 5, 6, 7. Okay, 5 to the power of 7. However, what is the rule? It's 5 to the power of 3 plus 4. So, when multiplying powers, with the same base, we add the exponents. Okay, it has to be like terms. So if this was 3 to the power of 3 times 5 to the power of 4, there's nothing we could simplify further. It has to have the same base. Okay, let's look at another example, and we're going to expand. 5 times 5 times 5 times 5 times 5 times 5, all divided by 5 times 5. Now we can cancel. We can cancel one from the top and one from the bottom, and continue and cancel one more. This leaves us with 5 times 5 times 5 times 5, and that's 5 to the power of 4. And again, we're interested in the 4, but how did we get the 4? This is 5 to the power of 6 minus 2. So when dividing powers, with the same base, we subtract the exponents. And make sure you subtract the exponent from the denominator from the exponent of the numerator. Okay, let's use the rule. For this case, we have 5 to the power of 2 minus 6. This gives us 5 to the power of negative 4. That's okay. When we have negative, it just means we put the power in the denominator. So it works. So let's look at a summary of the rules. A to the power of m raised to the power of n. We have a to the power of m times n. A to the power of m times a to the power of n. We do a to the power of m plus n. A to the power of m divided by a to the power of n. We have a to the power of m minus n. And a is not allowed to be 0 because we can't divide by 0. If we have a times b in brackets all raised to the power of m, we can separate that as a to the n and b to the n. Similarly, for dividing, a divided by b all to the power of n, we can have a to the power of n all divided by b to the power of n. And this time b is not allowed to be 0. If we have a to the power of 0, this is always 1 unless a equals 0. We're going to leave out the definition for 0 to the power of 0 for now. If we have a to the power of minus n, that's the same as 1 over a to the power of n. And again, a cannot be 0. And 1 over a to the power of negative n, so we can have a negative in the denominator. This is simply a to the power of n. And again, a does not equal 0. So let's try these rules with some more examples. This is 3 squared times a squared. And we have 9a squared. So we can simplify by squaring that. We have 4 cubed over b cubed. And we can expand this. This is 64 over b cubed. Here we go. We have a whole bunch of multiplies, all raised to the power of 0. So this is just 1, because anything to the power of 0 is 1. 15 raised to the power of negative 2. This is 1 over 15 squared, and you can expand this if you like. This is 1 over 225. We have 1 over 7 to the power of negative 2. This is just 7 to the power of 2. And this is 49. There's 2 ways of doing this. You can flip these both over, or you can just multiply. So we have 5 to the power of 6. Negative 2 times negative 3 is positive 6. Same for the denominator, 3 to the power of 6. And if you really want to expand this, 15, 625 over 729. And our last example. One thing we can do right away is just to expand the inside. So this is 8 over 4 to the power of 3. And if we do this, it eliminates the need to use the calculator. 8 divided by 4 is just 2. And now this is easy. 2 to the power of 3 is just 8. Now, we're going to be doing word problems, and sometimes we'll be supplied with a formula such as P equals 8,172 times 2 to the power of n. This is the base. This is not the base. This is just a multiplier. If the base is greater than 1, then it's a growth problem. If the base is between 0 and 1, then it's a decay problem. And n is normally in terms of a fixed amount of time, such as hours, days, years. So let's look at an example. An investment of $2,000 makes 4% per year and is compounded yearly. The total investment is found with P equals 2,000 times 1.04 raised to the power of n, where n is the number of years. How much is it worth after 8 years? Well, all we have to do is plug in 8 for n. So P equals 2,000 times 1.04 to the power of 8. We plug this into the calculator. So let's look at the TI first. And we have 2,000 times 1.04 raised to the power of 8. So our answer is 2,037.14. We round it off. Okay, that's how you use the TI. Let's look at the Casio. We have 2,000 times 1.04 raised to the power, that's this key, 8. And again, we have the same answer. We could be asked, how long would it take to get to $2,500? And you have to do a guess and test or use logarithms. So we already know that 8 years gives us more money, so we need less than 8. So we'll just try different values. 2,000, 1.04 raised to the power of 4. And that gives us approximately 2340. So that's too low. That's not quite 2,500. So let's try a bigger number. 2,000 times 1.04 raised to the power of 6. That gives us $2,531. So that's a little bit high. So let's just try 5 years to see if it's any closer. And that's $2,433. We don't need to do cents here because we're just checking the dollars to see which one's closer. And this is the closest to 2,500, so this is our answer. Okay, what are logarithms? Logarithms are the inverse of exponents. So again, this is not required, but try it if you can follow along. We have 2,500, that's our target. We put in our formula, 1.04 to the power of n. We need to isolate the power. So this is 2,500 divided by 2,000 equals 1.04 to the power of n. So the power is isolated. Now we take the logarithm of both sides. So this is log. This reduces down to 5 over 4 equals n, and the exponent goes up front. We put log 1.04. Now to isolate n, we divide both sides by log 1.04. Notice how I'm keeping the logs until the very end because I don't want any rounding errors. So let's just do this on the calculator now. We have log 5 divided by 4 divided by log 1.04. And it gives us 5.7 years. Okay, this is an algorithmic way to do it rather than guessing and testing, and it gives us a very accurate answer. And if we look between here, 5.7 seems very reasonable. And on the Casio, we can do exactly the same thing. Log 5 divided by 4 divided by log 1.04. And make sure your brackets match. And we get the same thing, 5.7 years. And that completes this lesson.